I can't show you the test because I'm in the middle of remaking it, but basically these are the same kind of problems you're going to see. The test is going to be mostly problems with the exception of those two questions you saw on the bottom here, which I guess anybody's not here. That's the whole review. So except for these three here, everything else is going to be a problem. There's not going to be any questions on the test, unless you include the derivation, all right, which is also technically not solving for anything. All right, let's do the strong acids and strong bases first. I'm going to do one of each, and this will be a really easy one. Won't even need a calculator for this because I gave you 0.001, and it's HCl, so it's monoprotic acid. So in a strong acid and a strong base, I still need you to lose points if you don't do it, have the equation down. So I have to write the equation, which for this guy is HCl plus H2O, as all acids do, forming hydronium ions, and in this case, chloride ions. Now, arrow goes one way on this guy. If you draw a double arrow, or if you try to solve these, as some people will, as equilibrium problems, you're going to obviously get almost no points for solving it as an equilibrium problem. Solving for X and all this stuff. I always get people who do that. It goes one way, 100%. So whatever I'm given over here, 0.00100 molar of that, I get 0.00100 molar of hydronium. I also get chloride, but I don't really care because I'm looking for hydronium, which is 0.00100 molar. I now have to solve for hydroxide. I know this one, that one's done. The hydroxide is going to be basically, well, I guess I'm starting from scratch. Kw equals hydronium times hydroxide, which I want you to show you the whole thing. So hydroxide is going to be Kw over hydronium, which would be 1 times 10 to the negative 14th molar squared over 0.00100 molar. Now, anybody who sees that number knows that's 1 times 10 to the negative third. So basically, hydroxide is going to be 1 times 10 to the negative 11th. Right? Everybody get that? Yeah. So you got your hydroxide, you got your hydronium, you need your pH, which is a negative log of the hydronium. Need to see all this work. Need to see the equation for each. Losing points if you don't. Negative log of 0.00100 molar. Again, because I made such easy numbers, and maybe one of them on the test I think probably is this easy. That's 1 times 10 to the negative third, so your pH is going to be 3. If you don't believe me, you can plug it into the calculator, but I think most people know that. 1 times 10 to the negative third, power of 10 is negative 3, negative in front of it, positive 3. And then the pOH. You don't have to show an equation for this. All you have to do is subtract, and you get 11. So it makes sense that a pH would be 3 for an acid. Yes. Matter of fact, on the test I'm just redoing it now. I can only have room for one blank on the test. In that blank next to that question, you should put in the pH, and I'll tell you to put the pH in both cases, in all the cases. Even though you're solving for 4 things, circle all those other answers. That's a good way of knowing whether you did it right. If you find you're solving for a base and you got a pH of 2, you probably did something wrong. And it's easy to do that because in the first case here, your first guy you get is hydronium. In the case of my next one, I'm going to do right now, the first one I'm going to get is hydroxide. You got to make sure you plug the correct one in. All right. So for this guy, it's going to be a little bit harder for several reasons. It's also different, not necessarily harder. AlOH3 does not react necessarily with water as much as it dissolves in water into aluminum ions and hydroxide ions. Okay, aqueous. All right. I have to balance it, so you have 3 in front of there. So I get 3 times the number of hydroxide ions as my concentration has told to me as 0.020 molar. Okay. There should be another 0 in here for significant figure's sake, because otherwise you won't be able to get the pH to the right numbers. You just round it off to a whole number. All right, so at 0.02, you got 3 times 0.0200 molar. All right, which of course gives me my first answer. My hydroxide is 0.0600 molar. All right. Now, same exact thing. You go through Kw. I'm going to shorten it up this time. Hydronium is going to equal 1 times 10 to the negative 14th molar squared over 0.0600 molar. When you do the math for that, what do you get for the hydronium? Anybody?
1.7 times 10 to the negative 13.
All right, so 1.7 or 1 point, probably some other. I did not have an extra 0 in there. Yeah, it's probably 1.67 times, but that's my fault for not having the 0 up there. Times 10 to the negative what? 13th, is it?
Yeah.
Okay. On a test, I'm making sure as I redo that I have all the significant figures right and everything else is correct. All right, so that's the concentration of the hydronium. That's the guy I got to plug in for my pH. All right, negative log of 1.67 times 10 to the negative 13th, which is what? 12.8. So 12.8. And therefore the pOH would be what? 1.2. All right, again, that's not enough work. I just did one showing you all the work a minute ago. This one I shortened up a lot. You should show me the equation. You should show me the equation for KW as well. All right. And otherwise, again, expect to lose points, especially if you make a mistake, because then I will not give you partial credit if you don't show that. I'll take off points for not showing the work, period. All right, but I'm not going to take off full credit if you have the right answers and it's clear what you did. All right, but if you don't have the right answer and you also didn't show the work, and it's easy to do that, then you don't expect to get basically any points. All right. All right, next one. Weak monoprotic acid, we're going to abbreviate as HA most of the time, with the exception of acetic acid, which I told you have to know. All right, acetic acid will be written out in the test CH3COOH. It's this H that ionizes and breaks off. All right, so I'm going to use HA for monoprotic acid. I want to calculate the Ka. I'm going to write my equation. HA plus water yields hydronium plus whatever the negative ion is. Told I have 0.0100 molar of that, 0 and 0 of that, minus X, this initial change in equilibrium, plus X, 0.0100 minus X, X, and X. Now, since this one's asking me for Ka, I basically better have some other information to find out what X is, and I do. In this case, I'm told I have the pH. By the way, there are several other things I can tell you on the test, and I will. And I do more than one of these, and one of them I might give you the pH, the other one I might give you the percent ionization, or I can just tell you what the hydronium ion concentration is. All right? So you saw all three of those in the homework and in the notes somewhere along the line. This one gives me the pH, which is probably the hardest one to do because you've got to remember to take, the hydronium is going to be the inverse log of the negative pH, which would be the inverse log of negative 3.47. So what does the hydronium, what does X equal when you did that?
2.39 times 10 to the negative 4th.
2.39 times 10 to the negative 4th, or 0.000239, or no? That's not what anyone else got. Let's see. Inverse log of negative 3.47. What do you get?
3.39 times 10 to the negative 4th.
Say it again. 3.39
times 10 to the negative 4th.
All right, so I just misheard it. Okay, 3.39 times 10 to the negative 4th. Okay. All right. So that's basically, or if you have 0.000339. All right, that's my X. I plug that guy in for here, and for here. So when I go to solve, I show the equation Ka equals hydronium times the negative ion over HA. So it's going to be, and again, at this point, someone will decide, oh, it's time for me to solve for X, and they'll put X's in here. It happened last test. It'll happen again this test. All right, you don't. You put in 3.39 times 10 to the negative 4th squared, basically, right? Over 0.0100 minus 3.39 times 10 to the negative 4th. All right, and you do the math for it. All right, you square that guy, you subtract this guy, you divide it. What do you get for Ka? 1.2. Should be another significant figure. 1.15 times 10 to the negative 5th. Is that right? So that's for Ka. All right. Again, I don't have time in the review. The other class only has a single period to do an example where I could have given you percent ionization. Say I gave you percent ionization. Say I said it was 3.47 instead of 3.47 pH, 3.47% ionized. What would you then do to get X? Yeah, multiply this guy by. Now be careful. If I said it was 3.47, do I multiply by 0.347? 0.0347. You always move this place over two spaces, right? If I said, and a lot of people do this. If I said it's 0.40% ionized, people will multiply by 0.40. It's 0.0040. You always move this place over two spaces to get the to get a percentage. All right. Okay. So there's that kind where I'm solving for Ka when I know what X is. Now there's this kind where I'm asked for X and I'm given Ka. All right. X being hydronium. Okay. So let's set this guy up. Ha plus water yields hydronium plus the negative ion. My Ha concentration is 0.050. On a test, you will not get anybody who can't use a simplifying assumption for. So all of your exponents will be small enough, all of your numbers will be large enough. All right, you'll be able to do that. Minus X plus X plus X. ICE. This time, of course, I'm given Ka. It's 3.5, that's 10 to the negative fifth. So Ka equals hydronium times the A over HA. So it's 3.50 times 10 to the negative fifth equals X times X over 0.0500 minus X. That's where I can use a simplifying assumption. I just get rid of him. And basically I'll get X squared over 0.05 equals 3.5. What does X come out to be? Anybody? Say it again. Say it again.
1.32.
1.32. Everybody else get that?
Times 10 to the negative 30.
Right. Anybody else get that?
Yep.
Okay. So that's what X is. You're, you know that's also hydronium. So that's the answer to one of your questions. Hydronium is that. Now you know the pH because you can get the negative log of the hydronium, which is a negative log of 1.32 times 10 to the negative third. And that's that. What's that? What's the pH? 2.88. Okay. And POH would be 14 minus that, which is what? 11.12, right? 11.12? Okay. So I got pH, I got POH, I got hydronium. Actually, a hydroxide, how would you get hydroxide? KW, you have to do KW equals hydronium times hydroxide. Sulfur, hydroxide, you can do that. And that will be the last one. Oh, and percent ionization is one more thing. What do I do for percent ionization? I take this number here, and what do I do with it? Divide it by the original, and then times by 100. Part over the whole times 100. What did you get for the percent ionization for that guy? 2.64 times anything or no? Just 2.64%? Okay. All right. Now, that's the longest one you could probably do, with the possible exception of, if you did it the long way, the buffer solutions. Did I put a buffer on here? Yes. Now, a buffer solution on this one, if I did it the long way, I would do two equations. I don't know if anybody did it that way. If you look back through your notes, you probably did. What's the short way to do this? Yeah, pH equals what? What does it equal? pKa plus the log of the salt over acid. Oops. Now that's the short way to do it.
Can you use that way?
Hey, absolutely. This would be a lot quicker to do. If you didn't do it this way, again, you'd have to write out the equation for the salt, the equation for the acid, add the two together in your initial for the acid, and then go through X and solving for all that stuff. And then finally finding X, finding hydronium, finding the pH. Okay, and that would be a pain. If you just do this, all you gotta do is the pKa, the negative log of the Ka, which is 3.50 times 10 to the negative 7th. Show me the work for that. Plus the log of the salt's concentration is 0.30 molar over 0.200 molar. All right, and if you do that, what did you get for your answer there?
6.28.
6.28. Did anybody not get that? Because a lot of times people make a mistake in the math of this. I don't know if that's right.
pH was like 6.6.
All right, let's see what happens here. pH is 6 point what?
6.63.
6.63. All right, let's see what happens here. Did you take the the negative log of 3.5 times 10 to the negative 7th was what? Did you do it? Anybody do it separately?
I did it separately.
Okay, so what did you get for this one?
For pH.
No, that's not what I meant. I meant, did you just do this number right here, or did you do? You did a long
No,
way.
I did that.
All right, well you did the long way. What did you get for your answer?
For pH, I got 6.6.
Yeah, so you got the same answer. Okay, but did anybody have the numbers for this? I'm trying to find where the mistakes were in the math. Anybody? So 6.45 if you do it separately. Plus, now you got to take 0.3 divided by 0.2. What's that?
I changed the flow.
And take the log of that.
1.5.
How much?
I think log of
Log of 1.5 is 0.17.
0.176. So that plus that should give you about 6.63. That's what you should have to do it separately. If somebody didn't get the right answer. Yeah. All right. So there's the buffer solutions. Now we've got. That's right. Back to this page for these guys. All right. This is the easiest one, I think, the most common sense one of the acids which are stronger or weaker. You're going to expect the stronger acid to be the guy who's actually got the weaker bond, because basically the weaker acid has a strong bond because it's going to be holding on to that H. Remember what an acid wants to do. Any acid simply wants to lose that H. So a guy like hydrogen fluoride, hydrogen fluoric acid, he's going to be really holding on to that H really well. So he's not going to be a very good acid. He's going to be a much weaker acid. So basically this goes by the opposite electronegativities. I would expect HCl to be a stronger acid than HBr. Is that correct? Did you all circle that?
HBr was valid.
Dang.
Contradicted what you said. Yeah.
Right, just said the opposite. I explained it correctly, just chose wrong.
Yeah.
Why? Because HBr is further down than HCl. All right, what about the next guy? Now here, this one's a little bit tougher because it doesn't make as much sense to us. We have to kind of just remember the oxidation number. The higher the oxidation number, what does that tell you? Stronger the acid. So if you have a stronger acid, who's got the higher oxidation number in this case? Remember how to do this. You have a -2 here. You have a +1 there. So it's a central guy that's going to be changing. What's the oxidation number of this guy? Minus, I heard somebody say +5. Okay. And over here? +3. Right? Okay. So 2 times -2 is -4, and 1 is 3. All right. So the higher oxidation number would be +5. Right? All right. Now, same thing's true for this guy. You have to kind of. It's not really a common sense one, but just you have to kind of just memorize. And it's kind of the you could remember this is the opposite of this one. Here, the electronegativities, as they got stronger, you got worse acids. All right. Here, electronegativities are stronger. Electronegativities, the better acids you have. Right. And so, who's better here? HCl3. So you should have circled him there. Okay. Finally, you have the derivation of the Henderson-Hasselbalch equation. I'm not going to redo that one. I'm going to show it to you because it's already done for you as of right back here. Where is it? There he is. Well, let's actually be easier if I do this. All right. Now, this is from scratch, okay? And there's only missing one thing on here. You have it all in your notes. But this is from scratch, and I would have you start with this, all right, on the test, if I had you do the Henderson-Hasselbalch equation. The reason I chose this one is, why would I want to choose this one? If you look at it, it already has pretty much all of HA is in here. Solving for, Ka is in here. It's just that it wouldn't have the salt above it. You would do this step and this step, all these steps up to and including here. That would be your derivation for Ka. Okay? If I were doing Kw, which I also said is a possibility on the thing, then what would have been different is this. Matter of fact, again, I can go back to it probably because it's probably done for me up here. For Kw, the difference is the equation. The equation is water plus water. Okay, it's not an acid adding a hydronium or adding a hydrogen hydronium ions. All right, so it's the same basic idea though. Rate forward equals this, rate reverse equals this. At equilibrium, the rates are equal. You bring the big difference here from previous chapter was that water comes over to the other side with the other constants because water is a constant, and that is what gives you Kw. Basically, Kw gives you hydronium times hydroxide. So there's three possible things I could ask you to do, and pretty much all of them start out with this much, okay? Except for what equation you're starting with. You're starting with that equation for Kw. You're starting with an actual acid, HA, plus water, if you're doing the Ka or if you're doing the Henderson-Hasselbalch. Also, Henderson-Hasselbalch would have the NaA as well, breaking up into sodium and the common ion thing. All right, so be able to do those for tomorrow, and that's it.